Hello everyone, I'm Dr. Priya Hassan and I teach at the Maulana Azad National Urdu University in Hyderabad, and I'm very thankful for the organizers to having invited me to give this talk to you on stars and their evolution. Now, I'm not too very sure about the level of the students, but I hope this will satisfy your. I will be giving you some Google form in which you can actually answer a short test and we can see how well you followed what we were talking about. Okay, so I'll be talking today to you about the physics of stars and their evolution. That's my email. You can always write to me at any time. If you want any questions or any help from me, you're most welcome to write. Now, the picture you see in the background is a very beautiful painting by Vincent van Gogh. It's called Starry, Starry Nights. And it basically is to convey to you that stars have fascinated everybody from time immemorial, not just scientists, but also artists and poets and everyone. They're just too beautiful. So let's start off with what exactly are stars. Now, many of you all may belong to the Lion King generation, so I'm sure you know these characters, Timon and Pumbaa, from the movie Lion King, where Pumbaa actually asked Timon, ever wonder what those sparkly dots are up there? So Timon says, Pumbaa, I don't wonder, I know. So Pumbaa says, oh, what are they? Timon says, they are fireflies that got stuck up in that bluish black thing. And Pumbaa says, oh, gee, I always thought they were balls of gas burning billions of miles away. And that's when Timon tells Pumbaa, with you, everything's gas. So you can actually see that this is a conversation, and I got this because though Timon actually thinks that Pumbaa is not, answering correctly, in principle, what Pumbaa says is exactly right. Stars are balls of gas burning billions of miles away. Now, another nice reference I liked, which is from the book Huckleberry Finn, if you've heard about it, it basically says it's lovely to live on a raft. We had the sky up there, all speckled up with stars, and we used to lay on our backs and look up at them and discuss about whether that they were made or only just happened. Jim here allowed they were made, but I allowed they happened. I judged it would take too long to make so many. So these are just examples of how stars have always fascinated people, even in prose and in art. And we'll now look at it from a scientist point of view. But I just wanted to bring to your attention that even a scientist, being a human being, also thinks about stars in a different way, not just by equations and how we study it, but they obviously mean much more to us too. So stars is basically a big ball of gas with fusion going on at its center, held together by gravity, right? And there could be variation in the stars, they could be massive, they could be sun-like, they could be low mass stars. Now, what are these big balls of gas basically doing? Like I mentioned earlier, they do what is called nuclear fusion. Okay. Now, nuclear energy, we know that we have nuclear reactors, and nuclear reactors basically produce energy by what is called nuclear fission. You have a heavy element, you break it into smaller elements, and that gives you out energy, which is how we actually run our nuclear reactors. But stars are actually the opposite process. They do what is called nuclear fusion. They take lighter elements, join it together to give you higher elements. So I'm sure most of you know this picture from nuclear energy, binding energy curve. That means what happens, supposing if you have two atoms A and B, you join them together, you get AB, but AB mass is less than the mass, individual masses of A plus B. Okay, and the difference in mass is what is called the mass defect. If we multiply that into C squared, you get the binding energy. So what happens if I fuse lighter and lighter elements? I end up with a smaller, a lighter resultant atom, and that difference will give me the binding energy, which you can see over here is like this. When I do fusion up to the level of iron, which has the atomic number 56. After iron, if I want to fuse heavy elements, I need to have energy provided to fuse it, right? Just think of it, you have two atoms and you're trying to fuse them together. Both of them have electrons in the outermost orbit, so when you try to jam them together, they actually repel each other. So if you have a high enough temperature, you can push them together and you can have fusion, right? And therefore for fusion, you do need a high temperature, a minimum of 1,000,000 degrees. Otherwise, you cannot fuse these atoms together. So that will happen only to the level of iron. And after iron, what you need some more energy source so that the temperature goes higher and these atoms actually collide and fuse together to give you your result of this thing. So up to iron is what a star can normally fuse, because here what happens is Fusion in this case is a exothermic process. You produce it and you give out energy. But after that, if you try to do it, if you try to fuse heavier elements, then it is an endothermic process. So it basically requires energy so that you can fuse it to actually give you the result. We'll come to this more in later these things, but you can remember that this is the basic principle of energy generation in a star, nuclear fusion, right? Now, what are the properties of stars that you note? If you look up at the sky, you'll see a difference in brightness, you'll see a difference in colors. And what is the most commendable thing about this is that this is a very tiny speck of light. So you can just think of it that how do you actually make sense of this tiny speck of light which you look at, which is what we're going to talk about today, the physics of stars and their evolution, because we actually use that very small amount of light coming from a star to actually understand the working of a star. So brightness we know as luminosity, right? And there are various sizes and colors of stars. So you have the sun is a more yellow star, Sirius is a more bluer star. You have these other stars. There's Betelgeuse over here, which is a red giant. So you have stars of different, here you can see the difference in sizes. If you see the sun compared to Sirius, it's this size. But if you actually see Sirius and you compare it to Aldebaran, you'll see it's so much smaller than Aldebaran. And if you compare Aldebaran to Betelgeuse, many of you all may know Betelgeuse, that's a star in Orion constellation. It's so much smaller than Betelgeuse, and Betelgeuse is again so much smaller than these stars. So you have a whole range in sizes of stars, and the sun is obviously a very ordinary kind of star. It's neither too big nor too small, nor too massive, nor too low massive. It's something in between. Now the colors of stars, these are the colors of stars. You can clearly see there are ones which are bluer, which are yellower, which are redder, and we'll soon come to it as to what do they mean. Now how do you understand these stars, right? So their first most important thing is what is called the Russell-Watt theorem. On a theoretical basis, this thing that for such a fusion reactor, the most important two things would be its mass and its chemical composition, right? That will actually define things for the star. Now, in the case of stars, when we observe it, we do not measure or we do not know very well the mass and chemical composition. So instead, what we observe is called the Hertzsprung-Russell diagram. I'll come to that in a bit, which basically plots the luminosity and temperature of the star. So what we'll first try to do is we'll try to understand what is this Hertzsprung-Russell diagram, because that is the basic, very, very basic diagram in stellar astrophysics, which is used to understand stars. Now, let's see what is the HR diagram, what do we mean by absolute brightness, what is temperature, and where are most stars, how do they evolve? We'll talk about evolution on the HR diagram. Now, just think of this basic problem. Consider you're a mosquito, right? And you actually look at this bunch of people over here and you're trying to understand what are their lifelines, right? So it's something like that. When human beings look at stars, right, and we are trying to understand their lives, it's something like a mosquito trying to understand a human life. How does that compare? A mosquito approximately lives, a male one lives for about 10 days, female for about 42 to 56 days. So if you say, let's say this thing lives, for example, let's say a human being is living for 80 years. So this is approximately the number, you have 18 to 365, divide by 10 if it's a male mosquito. So you can see a human life is approximately 3,000 mosquito lives, right? So if a mosquito wants to actually note the life of a human being and see how the life progresses, right, from birth to death, you'll need 3,000 mosquitoes to pass on the information to each other so that they can monitor the life of one human being, right? Which is obviously, you can see, it's a difficult process. And then it gets worse with stars, because if you were to look at stars, stars generally live a million years, which is 10 power 6, or they could live a billion years, 10 power 9, right? And a stellar life, therefore, is, you can see that it's much, much more than a human life. So we cannot actually look at a star from the time it was born till the time it evolves, till the time it dies. And therefore, the only way out is to use laws of physics to understand the lives of stars, because we can't see it from birth to death, right? So let's say the mosquito takes a Fallmer approach. It basically observes different properties for each person. For the sample of people, it says the color of hair, height, weight, age, different properties it observes. And basically the question it asks is, what are the major properties that define the human life cycle, right? And what do we notice in people when they want to assess, for example, their age? So if you were to plot a human HR, the simplest thing what we do is to plot height versus weight, right? The human. So let's say that would define the crucial parameter of age. So if I were to plot, you can see over here, if I were to plot height versus weight, I can see this is the section where the height is less and the weight is less. This is essentially when a human being is a child. And then when a human being is an adult, it's typically in this region where the height is somewhere between 1.5 to 2 meters and the weight may range from say 40 kg to say 80 kgs, right? That's the range. So that would be the HR diagram for human beings, which basically is a plot of what are the two important parameters of a human being which define the rest, right? So if you see a human being, you see their height and weight, immediately you know whether it's a child, it's an adult, you can estimate what is the age, how long that person is going to live approximately, and a lot of parameters about that human being can be defined if we just with a height weight plot. So the question is, how do you do a similar HR diagram for stars? What are the important parameters in stars? Now I already mentioned that as per Russell-Watt theorem, it is mass and chemical composition, which in the HR diagram actually is luminosity and temperature, and we'll see how does this come about. So today let us try to understand stars using the HR diagram. And the HR diagram is basically a plot of these two parameters, the absolute brightness of a star and the temperature of a star. And using this, we'll try to see how stars actually evolve with time. So first, let's give a bit better understanding to what do we basically need by brightness or intensity. Now, for stars, we have a scale which is called the magnitude scale, which tells us how bright a star is. Okay, this was done in the times when naked eye astronomy was done, and typically 5 magnitudes corresponds to about a factor of 100 in brightness or intensity. So if you see that each magnitude, if you take it to the power of 5, because it is 1 into 2 into 3, this thing, it will give you 100 to the power of 1/5, will give you 2.512, so that each star is brighter than the second one, right? And if we compare that in terms of intensities for a magnitude scale, this is how we put the magnitude scale. This would be intensity of star A by star B is 2.52 into MB minus MA, right? Now, so with that you can compare the brightness of stars, okay, with the magnitude scale. The next thing is, what is parallax? Parallax is something which we often use to measure distances to objects. Now a star, if it's very close to you, it may appear very bright, but you can have a star which is a very bright star which is very far from you, and hence it appears faint. And therefore it's very important for us to determine distances to stars. And therefore we have a parameter called parallax. What parallax does, the simplest way in which we measure it for a given star is, for example, you know the Earth is going around the Sun. The Earth's orbit has a distance of 1 astronomical unit, which is about 150 million kilometers. So if it looks at the star today in January, for example, you'll see it in this direction. After 6 months, you'll come to this side, and then you see the star, you'll get at another angle. If you measure this angle, right, this is twice of parallax. So let's half it. So if you half it, you can see over here, if I take tan of theta, if I take this one, if I take opposite by adjacent, you can see tan of the parallax angle, 1 AU divided by this gives you the distance. So if you actually measure your parallax in arc seconds, then your distance is 1 upon parallax angle, right? D is equal to 1 upon parallax angle. And based on this, we define what is called a parsec. So a parsec is the distance at which a star gives you a parallax angle of exactly 1 arc second, okay? So that is one of the units in astronomy which is based on parallax. So parallax is a very standard method of actually finding the distances to stars. We don't have the time today, but there is a European Space Agency satellite called Gaia, and Gaia basically is measuring the parallax of about 1 billion stars in our galaxy. By doing that, it's actually accurately measuring the distance to these stars. And the distance is obviously very important because you want to know the brightness of a star. If you don't know the distance, then it doesn't make any sense, because if the star is very bright and very far away, it appears faint to you. You do not know that it's a bright star. So you need to know the distance before you do anything else with that. So parallax, like I told you, is 1 upon distance, and using this parallax by motion deferred by 6 months, you can actually find the distance to a star. So this star will actually move in whatever way against the background stars. Okay, and this is it. So what happens is, if you actually look, when we measure brightness, we actually call it in terms of what is called apparent magnitude. Apparent magnitude is what you observe without doing any distance correction. If we don't correct for distance, we measure the brightness of stars and we get magnitudes like this. Obviously the sun is very bright, and therefore the sun has an apparent magnitude of -26. I must mention that the magnitude scale is a reverse scale. So minus 26 is very bright compared to, for example, plus 20. So the magnitude scale works in that way, that a lesser number is much brighter than a positive number. So here you can see the sun has an apparent magnitude minus 26. So it's very, very bright. But for example, the Venus has it minus 4, the pole star is 2. Our naked eye can see only up to about 6. And for example, with the Keck telescope or the Hubble telescope, you'll see approximately 25 to 30 magnitudes, right? So this is the magnitude scale. This we can measure, right, when we observe stars. So magnitude scale, like I mentioned earlier, was MB minus MA, 2.5 logs of this. So you can see on this scale, if you look at the apparent brightness, this is how it appears. But what is obviously very important for us to do is a distance correction. And that is what we call the absolute magnitude. So how do we do absolute magnitude? Absolute magnitude is the apparent magnitude of an object if it were at a distance of 10 parsecs. Okay? Then whatever is the brightness, that's what we call it. It's absolute magnitude. So if you now convert absolute magnitudes, then you will see in that case, you actually, the brightness of the sun is much lesser. So absolute magnitude, we convert it using this formula, which is mentioned over here. This is the apparent minus absolute is minus 5 plus 5 log d. So that's why if d is equal to 10, minus 5 plus 5 is equal to 0, that means apparent magnitude is absolute magnitude. And you can actually calculate the distance modulus. This is m minus m for a given star, if you know its distance. Stars also have velocities. They may move. Radial velocity is the velocity in the line of sight, which you can get from Doppler shifts. So if you do spectroscopy of a star, right, you see the spectral line will get shifted by some amount which is called delta lambda, and the delta lambda by lambda naught is equal to Vr by Vc, which actually gives you the radial velocity, which is the velocity of the star in your line of sight. Okay. In the plane of sky also, the star may move, right? And based on that, you can actually calculate what is the, so we can measure what is called mu, or the proper motion along right ascension and declination, which are the two coordinates with which we measure stars. And we can use that to find out the tangential velocity. And you can see that the tangential velocity and the radial velocity together can give you the space velocity. Okay, this is Pythagoras law. You take the root of the sum of the squares of radial velocity, tangential velocity, and you get the space velocity. Now let's get back to luminosity. Luminosity, like we all know from Stephen's law, it is proportional to, the flux is proportional to sigma t power 4, where t is the temperature of the star. And if the star is a sphere, right, it obviously depends upon the area of the star, which is 4 pi r squared. And therefore the total luminosity of a star is 4 pi r squared into sigma t power 4. That means if you want a star to be bright, either its radius has to be very big or its temperature has to be very hot, right? We'll come to this later on, because there are special stars we'll talk about whose luminosity is high, not because the temperature is high, but basically because the radius is high. And similarly, there are certain kinds of stars for which the luminosity is very low, though its temperature is very high, but its radius is very small. So we'll come to that in a bit. How do we measure the temperature of stars? Okay, so I'm sure all of you all have done the blackbody radiation spectrum, right? So to measure the temperature of star, we basically use the blackbody radiator, okay, assuming that a star is a blackbody radiator. Now, what is a blackbody radiator? We know that if white light, we split it into its constituent colors in the Vibgyor colors. We know that this is the whole electromagnetic spectrum, but our eyes can only see the optical path, which can be broken up into the Vibgyor, right? Now what happens is, if I take the spectrum of a star, I will know I have all the different colors, and I can measure the intensity of light coming in different colors, right? Which is plotted over here. So here what do I have? The intensity versus wavelength. So you can see that if I plot, this is for a black body, I can plot it, it comes something like this. So if the body is very hot, you will see this peak comes closer to the blue part, means shorter wavelengths. And if it is cold, its peak will come towards the redder part, which is longer wavelengths. So what happens is, if we observe an object for which we know its brightness in different colors, right, we can actually plot it like a black body and fit it and find out its temperature. So how do we do it for the sun? For example, for the sun, we measure its brightness in different wavelengths, right? You see the black curve over here. The black curve over here gives you the luminosity of the sun. Now I fit this to a black body curve, which is this mauve or pink curve, whatever it is. And when I fit these two, I can get the black body temperature of the sun. So now I know the surface of the sun has a temperature of 5800 degrees Kelvin because I fit this to a black body spectrum. But what you can see is that there are these things coming over. These are what are called emission lines, which you can see over here. And you see this dip over here, this is an absorption line. So there are certain wavelengths or frequencies at which there's an excess of emission. So those are emission lines. And there are certain wavelengths of frequencies where there's a fall in the emission, which is the absorption lines. So what we actually do is, if you look at a star, you break its light by the spectrum, get its light in different wavelengths. And then what we do is we actually pass this through what are called filters. Okay. What is a filter? This is an ultraviolet filter which lets in wavelengths close to 3600 angstroms. You have a blue filter with wavelength 4400 angstroms, a yellow filter with 5500 angstroms. And these filters have a width of this. So basically what you're doing is you're using this filter so that only light of this wavelength passes through, and then you can measure its brightness. So by doing that, what do you get? I can actually get these points on the curve. What do I want? I basically want to plot the intensity at different wavelengths, right? So that's exactly what I do when I pass this light through these filters. And then if I add up all the light from all filters, it is called bolometric magnitude. That means I add up all the light. But otherwise, we call these are what are called photometric systems. That means we have certain filters at which we measure the brightness of light coming from a star. Supposing there's an emission line at that particular wavelength, we can actually use our filter. Those are called narrowband filters, which are basically tuned on certain spectral lines so that we get to know the brightness at that spectral line. The broader filters, for example, these intermediate or wideband filters, which I showed you, these ones will get all the light in this wavelength. But with this, basically, we can fit it to a black body curve. So to fit it to a black body curve, obviously, you need at least 2 points, right? 1 point will not get me anywhere. I need at least 2 points and preferably even more. So the more points I have, the better I will fit this to a black body curve with which I can determine the temperature of a star. And if I know the difference, if in brightness, say in two filters, B minus V, I can actually determine the temperature. How do I do that? Because if I have this black body curve over here, I know its brightness here and I know it here. I know this is the black body curve, so I can actually see which line, which black body curve does this fit to, and hence I can find out the temperature of the star. So that is what we call color. Color is the difference in brightness in two filters, in two bands, B minus V, and that gives me the temperature of the star. So now we can plot our stars. We already saw how to do luminosity and how to do temperature. This one is spectral type, but let's do it with luminosity and with temperature. And this is what we call the HR diagram. Now, when we plot most stars which we know in this HR diagram, they seem to take a line like this, okay? This is the sun. This is mass of the sun, m sun. This is 0.3 times the mass of the sun. This is 3 times mass. So you'll see all these stars seem to be on the straight line, okay? And this straight line is what we basically call the main sequence, okay? Now, so typically stars like the sun or most bulk of stars are always seen along this line, which we call the main sequence. And therefore we say that since the star is spending most of its time fusing hydrogen to helium, basically the main sequence is that period in the life of a star when it's basically fusing hydrogen to give you helium, right? So with better telescopes, we have better calculations or better measurements of the magnitude of stars. So this is a better, this is from Hipparchus, which gives you the magnitude. This is with Hipparchus, and this is the color. The color, like I told you, is the brightness difference in two filters, okay? We said this was temperature because I told you earlier that here we had effective temperature over here, but the color is also a measure of temperature. And that is important because like you see in this diagram, all these quantities on the y-axis as well as the x-axis can be measured, right? we measure the brightness of a star, its magnitude, and we measure the color of a star, difference in brightness in two filters. So with that, we can plot off an HR diagram. What is the big advantage of putting a star on the HR diagram? The important part about HR diagram is once you place a star on the HR diagram, you can find all its other parameters, and I'll show you how exactly we do that. So for example, this is the main sequence, this is luminosity, this is temperature. You see the stars like this, okay? Now you'll see some amount of stars even lying here, some over here and some over here, right? Now, let us first talk about hot stars. Hot stars are bright, right? We know luminosity is equal to sigma 4 pi r squared t power 4. So hot stars are very bright. But the problem is hot stars are very rare. We do not have too many hot stars, okay? The most stars, red giants, are more common. So most common stars are the red dwarfs. So actually if you were to plot HR diagram of stars, you'll see most stars along this, which is called the main sequence. But you'll see some stars over here and some stars over here. We should also note an important thing about the HR diagram is that the temperature scale goes like this, okay? Magnitude scale also goes like this. It's a reverse scale in the sense what is over here is brighter, what is over here is fainter. Similarly, this temperature scale goes like this from right to left. So what is here is cold and what is here is hot, right? Now what happens is, therefore, if you actually see in the HR diagram, if you were to plot it, stars over here, these stars are bright, they are very bright. But you can see that their temperature is less, right? The temperature is less, they are cold. So we know luminosity is equal to sigma 4 pi r squared t power 4. So this t we know is small. So if we want luminosity to be high with t being small, then the radius has to be very large because we have a 4 pi r squared. So therefore if I want these stars to be, they are cold stars, if I want them to be so bright, okay, they have to be very big in size. R has to be very large. If you remember, luminosity is sigma 4 pi r squared t power 4. So these stars are very large and hence we call them giants. These are called supergiants and these are giants because they have lesser, here you see luminosity is lesser, so the corresponding radius is also a little lesser. Similarly here, look at these stars. These stars are hot, right? They are on the left part, but the luminosity is low. Again, we'll use the same formula. Luminosity is equal to 4 pi r squared t power 4. T is large, but luminosity is small, and that will only happen if R is small. So if R is small, we then call these stars dwarfs. So dwarfs are stars with small radii, while giants are stars with larger radius. So what happens is stars in the upper right are large, lower left are small. Okay? This defines only size of the star and not the mass. How do we find the masses of stars? Temperature increases to the left, and let's look at these. How do we get the masses of stars? If we actually look at families of stars, this is the main sequence. These are what we call supergiants, these are giants, here are the dwarfs, right? Temperature, I said here is low, here is high. Luminosity, here is low, here is high. So these ones, this will be, okay. This is in terms of magnitudes, yeah. So the HR diagram can also be used to measure the mass of a star, okay. How do we know the mass of stars? It's easiest for us to find it out in binary systems. How do we do it in binary systems? In binary systems, if you have these two stars going around, they are basically going around their center of mass, right? If you have two binary stars. So they go around their center of mass. If you can actually calculate the period, you can find the mass of these stars. And that's exactly what we do, exactly like the seesaw problem when two children sit on a seesaw. So what happens is if we were to plot stars for which we know the luminosity and we know the masses, say they are parts of binary systems, we can actually get a plot like this, okay. Note this is a log plot, okay, that's why it's coming as a straight line, okay. It's log over here and log over here, and then you are going to get a straight line, and the straight line has a slope of about 3, okay. This is the slope of this thing. So basically it's telling you that if I know the luminosity of a star, I can find out its mass. This is very important. Like I told you, with the color you can find out the temperature. From the luminosity you can find out the mass. And from Russell-Watt theorem we know that mass is a very important parameter for stars. So now look at our HR diagram again. Here is my main sequence. Here are the supergiants, here are the giants, here are the dwarfs. Size is growing like this, right? But luminosity is growing like this. So therefore this is how mass grows and this is how size grows. So a star over here is very massive, over here is low mass, here it has a big radius, here it has a small radius. So once I place a star on the HR diagram, I can directly tell you its mass, its size, its temperature, and we'll come to the age part. So this is the luminosity, this is the surface temperature, size goes like this, mass. So that's the basic physics of the HR diagram. Now what happens is, stars in different parts of the HR diagram are in different parts of their life cycles. So the main sequence, if you see this main sequence, it's basically difference in masses, right? And here you see this is difference in sizes. This is small size, this is large size. This is small mass, this is large mass. So what happens now, this is the end of part 1, let us see, this is part 1, I'll go on to part 2. Let us now see how exactly stars are born. So now we know the physics of how, when you look at a star, you can form its luminosity, form its color, you can actually determine its temperature, you can determine its size, you can determine its mass, which are the basic parameters which we need for these stars, right? So stars are basically born in what are called giant molecular clouds. These are made up of molecular hydrogen. They are cold clouds with a temperature about 10 to 20 Kelvin. They are basically made up of hydrogen and helium. So 75% hydrogen, 23% helium. The rest is heavy elements. Now, how does a star basically form? Now, this is also very interesting. If a nebula, if it had enough of mass, right? You know there are two forces. One is gravitational, which is collapsing it, and one is the gas pressure, which is going outwards. If it's a low mass cloud, the gravity is not much, the pressure is large, pressure wins, then the cloud expands. But if it's a high mass cloud, then the gravity is large and the pressure is not so much. So a cloud can actually collapse in its own weight. Now, I'm showing this for the benefit of some of the physics students. You can actually calculate, it was calculated by James Jeans, when will a cloud actually collapse in its own weight, okay? So what happens is if you have a gas cloud, the kinetic energy is given to you by N, 3 by 2 kT, and for a sphere, the potential energy is minus 3 by 5 gf squared by r. If you want the cloud to collapse, then this has to be, your potential energy has to dominate over the kinetic energy so that the cloud can actually collapse. And if you substitute this for clouds, what you will actually see is that this is the number of particles. You can actually derive this from this thing, that if there is something called a Jeans mass, and if your Jeans mass is equal to this, which is directly got from these two equations, which you have over here, if the mass of a cloud exceeds Jeans mass, then you can have a collapse of the cloud. Now, we don't have the time today. I'm going to give this to you as homework rather, that if you apply these equations, calculate what would be the values of Jeans mass, okay? So this is the Jeans mass, and therefore what happens is you need to have a very massive cloud so that it can collapse, okay? And therefore for stars to form, you want this big cloud to collapse. And when this big clouds collapse, what actually happens is, you can now see the stars cannot form in isolation because you have to have this massive cloud which will collapse to form the stars, right? And therefore what happens is stars actually form in groups, okay, which are called star clusters, and all stars were all field stars, for example, even the sun was born in a cluster. Now, once a star is born, it actually comes, this is the regions where it sits, it's cold, and not where, and this is the luminosity, and gradually as the collapse takes place, it becomes hotter and hotter on these Hayashi-Henniet tracks, and it comes on the main sequence. So the zero-age main sequence is when the star just arrives on the main sequence. I'm sorry I'm like running through a few things, but since we have a time constraint, I am like rushing through it. But since you have the recording, you can repeat it and see parts you don't understand. Okay, so what happens is, these are the tracks which are called the pre-main sequence tracks while the star is still forming, okay? So it may come downwards. When it's coming downwards, it's basically, you basically have the fallen luminosity, right? And here as it's going towards this side, it's basically becoming hotter. Finally, for a star to be born, you need it to become hot, because only if it is hot can you have nuclear fusion, right? Like I told you earlier, for nuclear fusion, you need a minimum of 1,000,000 degrees. So you have to go towards this part, towards the left part of this, so that the cloud becomes hot and actually does nuclear fusion, right? Now, through most of the life, stars are basically converting hydrogen to helium, because 75% of the star is hydrogen. So the core of the star is basically converting hydrogen to helium. And energy production, the simplest one which happens in the sun is called the proton-proton chain. So you start off with 4 protons, you join them together. You can see, like I told you earlier, the final mass is lesser than the initial mass which we got from 4 protons. And that difference is what we call the mass defect, which is this. And if this mass defect I multiply it into c squared, I basically get energy. So this is the amount of fusion energy which you get through the proton-proton chain, which is the simplest process which happens in the sun. Now, other fusion reactions also can happen, not only in the sun but the other things. In the sun, 90% is proton-proton, but you could have fusion of heavier materials. For example, there's the carbon-nitrogen-oxygen cycle. There is also what is called the triple alpha reaction or helium burning, because 4 helium is 4, so 3 into 4 gives you 12, and that gives you carbon, right? So what happens is you just add on and you get more. So for example, 4 plus 12 plus 4 gives you 16, that will give you nitrogen, and you can proceed in that way. Now mass is a very important driving factor of stellar evolution, because what happens is the more massive the star is, the better it will collapse. And if it collapses more, the temperature will become higher. If the temperature becomes higher, the fusion reactions it will do will be more effective. For example, triple alpha or CNO cycle. For example, the sun is not very hot, it's only 1,000,000 degrees, and therefore it can live for much longer. The sun will live for 9 billion years because it is burning its hydrogen very slowly. But for example, if I had a star which had 40 times the mass of the sun, it will fall and give a much higher temperature. Because of that, it's going to do much faster nuclear reactions, due to which the star will burn off much faster in 1,000,000 years. And therefore, the mass is very important to tell you how long a star will live. So actually, it's a little counterintuitive. A more massive star will die very fast, less massive star will live longer. So as the stars start burning their thing, they start moving away from the main sequence. This is the HR diagram. They move on the right. They become colder because the fusion stops, right? So they this thing. Then what happens if the fusion stops, right? The star becomes colder, right? Then what happens is the collapse takes place better because the star is colder. Kinetic energy is lesser. Potential energy will dominate. The star will further collapse. It will get a higher temperature in a core. Therefore, after burning hydrogen, it will start burning helium. Then when it finished helium burning, again there's no gas pressure outwards, right? So the star will collapse better, it will get even more hotter. So then it will burn, for example, triple alpha or 3 alpha to give you carbon. So depending upon the mass of the star, you will keep on getting higher and higher temperature, and heavier elements will get fused. So what happens is you start off with hydrogen, you have this hydrogen covenant helium, then this lower inner part further collapses. You will get carbon, then you further collapse, you get oxygen, you further collapse, you get the heavier and heavier elements. So it's like an onion shell-like structure which you actually get, where you have iron in the end. Remember I told you the central part will be iron, outer parts are the lighter elements, and you actually do it in this thing. And then what happens? Is that the end? No, it's not. Because let's look at our sun, for example. It started off as a protostar. This is the sun. After another 4.5 billion years, when the sun finishes burning its hydrogen, it will swell up, okay? It will form what is called a red giant, because the outer layers will expand, cool and shed less brightly. This outer part will go away, it's called a planetary nebula, and the core of the sun will be left, and it will form what is called a white dwarf, okay? White dwarfs are hot, but they are dwarfs, so therefore their brightness is not too much, but they are hot and small. So typically the sun on the HR diagram, this is the HR diagram, it's going to move away on the right, it will become colder, it will become planetary nebula, it's going to let out its outer things, and then the core will become a white dwarf. Okay, so when the sun swells up, it's going to go beyond the the orbits of Saturn. So that's more than this will happen only at 4.5 billion years. So don't worry, not very soon. It will go out, and you'll have the sun swell up till the orbits of Saturn. So the Earth will obviously be engulfed in that. But by then we may be gone. And this outer region is what is formed a planetary nebula. Now this has got nothing to do with planet formation, but the first time it was observed, people thought it was a planetary system in formation, but it's not. A planetary nebula is the end stage of a life. If the star is even more massive, then what happens is when this expansion takes place, it takes place with an explosion, okay? And that explosion is called a supernova. So if the star is, for example, 8 times brighter than the sun, then this explosion takes place. This outer shell will throw out, it forms a shock, okay, it's called the supernova. And this central part, which, for the example, sun is forming a white dwarf, this forms what is called a neutron star, okay. A neutron star is a very small star. It barely has a size of 10 kilometers, but it has a very high density. It has a very high density and a very strong magnetic field. So supernovae are very rare because basically we didn't talk about it, but when stars are formed, high mass stars are very less. They are more low mass stars. So you have very little high mass stars in the galaxy. So you'll have very few supernova forming. But when they do happen, they are so bright that they can be as bright as a whole galaxy. So if you look at a supernova in another galaxy, it's very easy to observe it because it's very bright. And that is very important because it can be very well used to study that galaxy. For example, get the distance to that galaxy and study other features about the galaxy. We don't have time about it today, but even the study of the acceleration of the universe is based on supernova studies. Basically because supernova in other galaxies can be well observed. And you, for example, I wanted to tell you this, is that you are basically star stuff. So what we saw is a star is a fusion reactor, which is fusing things till iron, till 56. So you have this fusion taking place, and then all heavier elements heavier than 56 are formed only when a supernova blast takes place. So when a supernova blast takes place, then you fuse heavier elements, which is again what tells you abundance. Why do we have lesser amount of heavier elements? Because they are only formed because it's an endothermic process. It will only be formed when you have a supernova, for example, and that's when you will get this thing, right? But all the carbon, all the phosphorus, all the calcium in you essentially has been fused in a star, right? Because the universe is basically hydrogen, helium. What we are made up of carbon, nitrogen, oxygen, calcium, things like that, that is basically got fused in a star, right? So we are essentially star stuff. Like I told you, the universe is basically hydrogen and helium, but human beings, our composition is very different from that. So we are actually made of stardust. That's what our composition is. So a very interesting way of looking at the periodic table, I'm sure you've seen it, but the other way of looking at the periodic table from an astronomer's point of view is by fusion. How did all these elements come about in the universe? We know the universe is basically hydrogen and helium. So if you form all these other elements, they basically formed by some processes happening in stars. We don't have time to go about this, but you can basically see the different processes through which things are created, and how do you actually get all the other elements, right? Now we'll go back to the massive stars, where remember I told you the central part forms what is called the neutron star, which has a very small size, a very strong magnetic field. And this is how the star is, because it has a very strong magnetic field. The light only comes out from its poles, okay? And therefore these stars are called pulsars, because we look at it, light will come in a pulse, now a pulse, now a pulse. So you actually see it in pulses. The first time they were observed, people actually thought this was some extraterrestrial signal coming to us, which had a certain periodicity. But then it was realized this is a purely natural phenomena. You just have this core of the star, which is very massive, and of a massive star which has a magnetic field, and therefore the light only comes out from these, it's like a torch. If you rotate it, and light is coming only from two different ends. So this is a neutron star. And if the star is even more massive, then this same thing which formed the neutron star, which actually form what is called a black hole. A black hole is something which collapses in its own weight totally, so you end up with a zero size, okay? It ends up with a zero size where the whole thing collapses in its own weight because it's so massive. And through a little bit of physics, we won't talk about it today, but you can actually calculate what could be the masses of white dwarfs, etc., and neutron stars using the Chandrasekhar limit. Now, black holes are also very interesting objects. Stars can form black holes, but not only that, in the center of most galaxies, we do find supermassive black holes. A massive black hole has a mass of about 10 power 6 times the mass of the sun. A supermassive black hole has 10 power 9 times the mass of the sun. We know that our galaxy itself, the Milky Way, in its center, we have a massive black hole, which is about 4 into 10 power 6 times the mass of the sun. So the question is that what do black holes have to actually do with the formation of galaxies? That's yet another question which we still need to answer. So let me just wrap up with how do we actually have the birth and life of stars. You have a collapsing cloud, which actually satisfies Jeans criteria. By Jeans criteria, you need basically a cold and dense cloud, which lets the potential energy dominate over the kinetic energy so that you have a collapse. Once you have a collapse, you form a new star. And if it is a sun-like star, it will evolve to give you a planetary nebula and the white dwarf. And If it's a more massive star, it will actually give you a supernova remnant, a neutron star, and a black hole, right? Now, finally, in the end, I'll talk about what I actually work on. I work on what are called star clusters. Star clusters are groups of stars which are formed from the same cloud. Okay? So, therefore, these stars are all at the same distance. They are formed from the same cloud. They have the same chemical composition. They only differ in mass. So, you basically find the HR diagram of cluster looking like this. And what makes these clusters very interesting is that now you see all these stars differ in mass and they are going to evolve differently just because of their difference in mass. So therefore, what you can see over here is that if you have a young cluster where everybody is sitting on the main sequence, first of all, the most massive stars, remember I told you the massive stars die fast before the low mass stars. So the most massive stars will move towards the right? They'll move towards the right. These stars will come over here. As the star becomes older, these mass stars will move to the right, and then these ones will move to the right. And therefore, there isn't an animation over there. So you can see it moves away in that way. And this is a very important thing because this can be used to actually find out the ages of clusters. Okay. So in a cluster, they all have the same distance. So if you actually observe them and you actually see which is the last star which is sitting on the main sequence, you can actually see what is the mass of that star and what is the age of this cluster, so that this much star should be sitting on the main sequence, and that will give you the age of the cluster. Once you know the age of cluster, you know the age of all the stars. So therefore, to understand stars, the physics of stars, all we need is an HR diagram. We need the magnitude of the star, we need the color of the star, we need the distance to the star. And once we have these parameters, we can place the star on the HR diagram, right? And once you put it on the HR diagram, you will know its mass, its size, its temperature, and through this method with star clusters, you can actually find out its age. So that gives you the whole story of evolution of stars just through the HR diagram. So stellar astrophysics is in a much better situation because we have the HR diagram with which we can find out parameters for stars. But if we actually move ahead, when we come to galaxies, we do not have an HR diagram like that. And therefore, with galaxies, the evolution story is more complicated. But we'll talk about that when we meet again. So thank you very much. Bye-bye.